I am going to explain experiment on the resonance characteristics of microstrip ring resonator and computation of dielectric constant of the substrate. The aim of the experiment is to determine the resonance characteristics of microstrip ring resonator and to calculate the relative electric constant, that is epsilon r, of the substrate. The objective of the experiment is to understand resonant characteristics of ring resonator. The operators required are microwave signal source with modulation, which ranges from 2.1 to 3 GHz, 3 dB attenuator, coaxial detector ranges from 2 to 3 GHz, Vswr meter, which is voltage standing wave ratio, microstrip ring resonator ranges from 2 to 3 GHz, and connecting cables. This is the layout of microstrip ring resonator with inputs and output lines. This microstrip ring resonator, it is formed by bending the strip conductor of a microstrip in the form of a ring. So this figure shows the configuration along with input and output feed lines. The gap between the feed and the ring determine the coupling. Resonance is established when the mean circumference of the ring is equal to integral multiples of guide wavelength in microstrip. After the connection, here this ring resonator provides a simple experimental means of characterizing a microstrip substrate. Epsilon r has to be calculated, that is relative dielectric constant of the substrate. So to calculate that, we have a formula 2 pi r is equal to n lambda, which is equal to n v naught by fx square root of epsilon effective, for n is equal to 1, 2, 3, where r is mean radius of the ring, n is mode number, lambda g is guide wavelength in the microstrip, and epsilon effective is effective dielectric constant. So epsilon r has to be calculated using this formula, that is 2 epsilon effective plus 1 plus 10h by w whole over minus of minus 1, which is simplified as 1 plus 10h by w whole over minus of plus 1 to the whole power minus 1. So here V naught is the free space velocity, epsilon r is the resonant frequency of the ring, h is height of the substrate, w is width of the substrate, fr is resonant frequency of the ring, and epsilon r is relative dielectric constant of the substrate. The connection has to be set up as shown in the figure. Here, assemble the setup like this. Insert ring resonator, this is the ring resonator, between P and Q, with port 1 as input port connected to P and port 2 as output port connected to Q. Keep the RF source level and Vswr meter gain to maximum level. Vary the frequency of the source slowly from 2.2 to 3 GHz and note the frequency at which Vswr meter shows a peak value, and this is the resonant frequency, that is Fr of the resonator. Calculate the effective relative dielectric constant. This is the tabular column to note down the measured data to identify resonant frequency. So the frequency ranges from 2.2 to 3 gigahertz. For 2.2 to 3 gigahertz, note down the corresponding VSWR meter reading and calculate H, W, R, FR for n equal to 1, V naught, epsilon effective and epsilon R. The outcome of the experiment is, after the completion of these experiments, students are able to understand the resonant characteristics of ring resonator. Now, let us move on to the demo part. Today I am going to show you the demo of microstrip ring resonator. For the microstrip ring resonator, we need ring resonator, detector, which is a 3 dB attenuator, RF cable and VSWR meter. This is the VSWR meter. VSWR stands for voltage standing wave ratio, VSWR meter, to check the output, and this is S-band signal source which gives the frequency from 2 to 3 gigahertz, and we need connectors. So initially the setup has to be set as shown here. First, keep the microwave signal in AM mode. Initialize the detector connected with the cable to the VSWR meter for the initial setup. Now, after 3 dB attenuator, connect a cable with the ring resonator. Before connecting the ring resonator, we have to adjust the VSWR meter using detector. So to adjust the VSWR meter using detector, initially this has to be kept in AM mode, then vary the frequency from 2 to 3 gigahertz. As the frequency is varied from 2 to 3 gigahertz, here we can observe the VSWR meter reading is changing. As you can observe, the VSWR meter reading is changing. Now, you can see the reading changing from 2 to 3 gigahertz, variation in the frequency. This is the initial setup we have to make to do the connection for ring resonator. Now, the setup is done for ring resonator. Here, ring resonator is connected to an attenuator, and the attenuator is connected to a VSWR meter, and the output is noted in the VSWR meter. Here, vary the frequency from 2 to 3 gigahertz. Initially, by using the attenuator value, we have already set the gain. Now, vary the signal source from 2 to 3 gigahertz. As we vary the source from 2 to 3 gigahertz, we can see the variation in the VSWR meter reading. Here, second VSWR meter reading, which is the red line one, has to be noted. As the VSWR meter is varied, there is a change in the VSWR reading. So, vary the frequency from 2 to 3 gigahertz and tabulate the readings.